Hi everyone. Today we are going to discuss motion in two dimension. Before going further in motion two dimension, let's just have a quick reminder in motion in one dimension. In motion in one dimension, we mentioned two types of motions: horizontal motion, like a car moving in a straight line. Another type of one-dimensional motion we mentioned is a free-falling objects. In motion two dimension, situation is a little bit different. Object is moving here in two dimensions, in x and y at the same time. Let's have this model. As we can see here in this model, this billiard ball is moving in the xy plane. In this situation here, this ball here has two components, one on x-axis, the intercept with the x-axis, the other one is the intercept with the y-axis. Okay, this ball here, as we can see here, is moving along this one here, and this vector here is the position vector r. Let's just name it here position vector r. The intercept with the x-axis is the x-axis, and the intercept with the y-axis here is the y. The position vector r in this case, it's equal to xi hat plus yj hat. So two coordinates were used here to represent the position vector for an object moving in two dimension. Remember here, x and y coordinates is in the horizontal direction, which means it's parallel to the surface of the earth. So let's here identify the position vector r equal to x I hat plus y j hat. Here it's called position vector. Now, when an object is moving between two positions from r initial to r final, in this case, the displacement r equal to r final minus r initial. Let's see this model here. In this model here, as we can see, this one here, an object, this billiard ball, is moving from position r1, let's just write it down here, or r initial here, to r final. This is our final position. So the displacement, which is in this case this vector here, just move this one here, it's this one directed this way here. So the displacement here, displacement delta r, it's equal to r final minus r initial. It's a vector, a quantity here. Now, same as before, we have an average velocity. Average velocity here, it's equal to delta r divided by delta t. Now, average velocity here, it's in two-dimensional motion. In this case here, which equal to delta v equal to r final minus r initial divided by t final minus t initial. And again, the instantaneous velocity or speed here equal to limit when delta r over delta t, when delta t here goes to 0, or the first derivative for r with respect to time t. One more thing here, the average acceleration, in this case, it's equal to same rules as before, but this one it's in two dimension. It's the delta v by delta t, and instantaneous acceleration here, it's equal to limit when delta t goes to 0, when delta v by delta t, or the first derivative of velocity with respect to time. Or we can say that in other words, here it's d2r by dt square, as in here. Since the position vector r is defined as xi hat plus y j hat. So delta r in this case here, it's equal to x final. In this case, it's equal to x final I hat plus y final j hat, this one here, plus x initial I hat plus y initial j hat. This case, let's rearrange the outcome here. It's equal to x final plus x initial in the I hat plus y final plus y initial in the j hat. This will lead us to this assumption. Rather than working with position vector r, we can work with x and y. So we can deal with the problem as two separate problems, one on x and one on y. So can be applied here, the same equations, same everything, and instead of working with one dimension here, we will work with two dimension, one on x and one on y. So the same 5 equations we learned in one dimension can be applied here easily. As we can see here, two sets of equations, one on x, as you can see here, and the other one it's on y. And remember, x and y here, it's in the horizontal direction, so there is an acceleration on y and acceleration on x. Now the common factor between these two sets of equations is time. Time here is the common factor. It's the same for both x and y coordinates. Once we find the position vector r, we can just identify the average velocity. In this case, it's equal to delta r over delta t. Let's have an example. The position vector of a particle is given by this equation here. R of t, it's equal to t square I hat plus minus 4t cube j hat. This one here. Okay. A, find the average velocity during the time interval 1 and 2 seconds. In this case, the average velocity, here, just let's move this one here. Average velocity equal to delta r over delta t. So we need to find, or in other words, it's r final minus r initial divided by t final minus t initial. Okay, in this case, r final equal to the position vector when t equal to 2 seconds. You just substitute t 2 seconds here in this equation here, and find that r final when t equal to 2 seconds, it's equal to 4 I hat minus, now 32 j hat. Now r initial when t equal to 1 equal to, in this case here, I hat minus 4 j hat. In this case, delta r by delta t, which in this case it's average velocity, equal to 4i minus 32j minus I plus 4j divided by, in this case here, 2 minus 1. In other words, it's equal to 3i minus 28j. This is the average velocity. Now B, find the speed of the particle. In this case, the speed is actually the magnitude for v when t equal to 1. In this case, v here equal to the derivative, first derivative of r with respect to t, which equal to 2t I minus 12t square j. You substitute 1 back in here, v equal to 2i when t equal to 1, here 2i minus 12j. So s here, the speed that's what we're looking for at t equal to 1 is actually the magnitude for this vector here. It's 2 square minus or plus minus 12 square. Let's have another example. An object has an initial velocity, it's given here, 2i minus 3j, and an acceleration 2i plus j. Find the velocity vector of the object at t equal to 2 seconds. Here, from the given information, v initial here, now v initial x equal to 2, this one here, and v initial y equal to minus 3, the magnitude. Now same thing here for the acceleration, ax here equal to this one here, 2, and ay equal to 1. So we have here, we set all the information, we have everything here. Now at t equal to, find the velocity vector. In this case, let's use the equation of motion here, vx final equal to vx initial plus axt, xt here, and we substitute back here t equal to 2 and v initial x, it's equal to 2 and ax equal to 2. In this case here, it's equal to 2 plus 2 multiplied by 2. This is v final x, which equal to 6. Now v final y final, in this case here, it's equal to v y initial plus ay t, in this case v final y when t equal to 2, it's equal to minus 3 plus 1 multiplied by 2, which equal to in total minus 1. So the velocity vector v when t equal to 2, in this case here, equal to 6i minus j. All what we mentioned so far is motion in the xy plane, and both x and y is in the horizontal direction. It's parallel to the surface of the earth. Now we'll mention another type of two-dimensional motion. It's a projectiles motion. Few assumptions we have to consider before working with projectiles motion. The first assumption here, there's no acceleration on x whatsoever. There's no air resistance, and acceleration on x, it's equal to 0. The only acceleration we have here in the whole process is g. It's in the y direction and equal to minus 9.8 meter per second square, or sometimes equal to 10 minus meter per second square. And remember the minus sign here because it's directed downward. Since ax equals 0 in this case here, it means velocity on x is constant all the way. So v initial or v final x equal to v initial x. It's constant. Rather than working with 5 equations, this assumption here end up with only one equation. It's x final here equal to x initial plus the initial x t. No acceleration, no half at square, it's all equal to 0. On the y-axis here we have three major equations: y final equal to y initial plus the initial y t minus half gt square, and v final y equal to v initial y minus gt, and the final square y, the initial square y minus 2g delta y. In summary, to work with projectiles motion, we have only one equation on the x-axis, three major equations on the y-axis here. Remember, time is common factor between both x and y. Let's have this model. In this model, as we can see here, a ball is fired with some angle here, it's theta, and initial velocity 2.67 meter per second. The black arrow here is the acceleration. As we can see, it's always downward all the way. Now, moving further, let's just here. To move further with this projectile motion, as we can see here, the velocity is decreasing. The y component is decreasing while the x component remains the same all the way. Now, again, the y component decreasing and the x component, it's constant all the way. At the maximum height, this one here, it's always at the maximum height, the y component becomes 0 and the x component remains again the same. Look at the trajectory of the ball here. It's taking the path like this. As we saw in the model, the trajectory is parabolic. When we fire an object, the ball was fired, this one here, it moves like this one here, and this track here is parabola. This is the maximum height here. Okay, so let's prove this one here. X final equal to v x initial t plus x initial, and since x initial and y initial getting on the origin 0 0 in this case here, so x final equal to v x initial t, or now this is the v initial and this is theta, v initial cosine theta times t. Now in this case, t here equal to x, no need to say x final, just x divided by the initial cosine theta. If we substitute this time here back in the y equation, so y final equal to, again, y initial, it's equal to 0, v initial y t minus half gt square. You substitute t back in this one here, you end up with y, no need to say final in this one, again, tan theta x minus g divided by 2 v initial square cosine square theta, this multiplied by x square. If we deep look into this equation here, it's similar to general formula for the parabola y equal to ax minus bx square, and this is the parabola equation. So the trajectory is the parabola path. Back to the model that we just mentioned. As we can see here, the object has initial velocity. Let's just do this one here. Initial velocity, it's the initial, and this is theta. So the y component, this one here, the y component, equal to v initial sine theta, and the x component here equal to v initial cosine theta. And remember, this x component here is constant all the time. Now the one is changing is the y component for this one here. Now let's just have a model here. Start with this one here. This here, just here, seconds before. This is the maximum, this one here. This is the maximum height, and this is the range, this one here. This is actually the range here, the horizontal range, and this is the maximum height. Remember, at the maximum height, the final y equal to 0 and the final x equal to the initial x. It's constant. When firing an object from ground and reaches back to the ground, the maximum height is defined as the initial square sine square theta divided by 2g, and the range r is defined as the initial square sine 2 theta divided by g. Notice that if you fire the object with 15 degree, you will get the same range as you fire the same object with an angle equal to 75 degree. Because if you look at the range equation here, in this one here, it's sine 2 theta, sine 30 is the same as sine 150, 70 multiplied by 75 multiplied by 2. So the same range you obtain for 15 and 75. But for the height is absolutely different. It's for the 75, it will be much larger than the 15 degree. Okay, again, 30 degree, you will obtain same range as 60. Now, to have a maximum range, you should fire the object with 45 degree, exactly 45 degree. So 45 multiplied by 2, it's 90. Sine 90 equal to 1, and this is the maximum value for this sine. So the maximum range will be obtained upon firing the object with 45 degree. This diagram here summarizes what I just mentioned before. As you can see here, 15, it's the same as 75, and 30, this is 30, it's not 60 by the way. Let's just do this one here. Okay, and this is 60 here. This one is 60, and this one is 30 degree. And as we can see here, the maximum range we obtain here when we fire the object with a 45 degree. Let's have an example here. Example: an object is thrown upward at an angle 30 degrees above the horizontal from height 2 meters with initial speed 10 meters per second. What is the speed of the object just before it strikes the ground? Before solving this problem here, let's just have this model. This situation here is similar to the situation in the example. This object here is thrown with initial velocity as you can see here, and this one here is the y component for the initial velocity, and this is the x component for the initial velocity. The object in this case here is thrown with some angle 39 degree. As we can see here, x is constant all the way, and at this point here, maximum height here, the y component equal to 0, and the only velocity component dragging this object here is the x component here. When we move further in this situation, the y component start increasing, but in the negative direction. Again, the x component is the same. And in the example, we need to calculate the velocity of the object just before it strikes the ground. In this case, it's somewhere here. Yes. So we need to calculate the velocity of the object or the ball here just before it strikes the ground. Let's back to the example. Here's the situation. The height is 2 meters. As we can see, is the height, this one here. If we set up the y initial at the top of the table here or the desk here, so the y final equal to -2. And remember, minus because it's below the reference point. The initial velocity here is 10 meters per second, and it's thrown with an angle 30 degrees. Now to calculate the speed is actually the magnitude for v, which equal to square root of v final x square plus v final y square. Remember, the final x here, it's equal to the initial x. In projectiles motion, v on the x component for velocity is constant. Now we need to calculate now the v final y. Use this equation here, equal to the initial y square minus 2g delta y. In this case here, it's 100 because it's 10 sine 30 square minus 2 10 minus 2 minus 0 equal to v final y square, and simply you will find v final y equal to 8.01. In this situation here, the initial x equal to the initial cosine 30, which in this case equal to 8.66 meter per second, and this one here is meter per second. You substitute s here equal to square root of 8.66 square plus 8.01 square, and speed here it's equal to 11.8 meter per second. And this is the speed just before it strikes the ground. What if we want to calculate the time required or needed for the object to strike the ground? To calculate the time, use this equation here. Y final equal to y initial plus v initial y t minus half g t square. You substitute back the initial y, in this case it's equal to 10 sine 30, and y initial here it's equal to 0. Now y final here it's equal to -2, so -2 equal 10 sine 30 times t here minus half 10 t square. This is a quadratic equation. You solve it, you will find two roots. Upon solving this quadratic equations, you will have two roots, positive 1, this is positive root, and negative root. Since time will never be negative, so we'll take just the positive root. One more example. An object is thrown from the top of a building of 60 meters height with initial speed 13 meters per second in the horizontal direction. Find the horizontal distance when the object strikes the ground. Before solving this example, let's have this model. This model here mimics the situation that we would like to solve. As we can see here, the object is fired. Here, the object is fired with horizontal velocity, like in this one here. Now, as we can see here, the object will strikes the ground. What we look for is the horizontal distance just when it strikes the ground. This is the horizontal distance here. Remember, this is not range. The range is calculated from air to air or ground to ground. It's not from air to ground. So the situation, it's like this. So this is the building with height 60 meters, and this is the ground here, and the ball is fired, or this object is fired horizontally like this, and with initial velocity 13 meters per second. The ball will strikes the ground here, and what we look for, we need to calculate the horizontal distance. This is x final. Now, to solve this here, remember, the ball is fired or thrown in horizontal direction, which means the initial x is actually, it's the initial, which equal to 13 meters per second, and the initial y, in this case, it's equal to 0. No vertical velocity component in this case here. So x final, in this case here, that's what we need here, equal to x initial plus the initial x, which is in this case, by the way, it's the initial t. Now, in this equation here, remember, if we consider this is the origin, so this is 0, 0 here, x initial is 0, so x final in this case equal to 13 t. So still missing the time in this equation here. To find the time, use the y equations. So y final equal to y initial plus the initial y t minus half g t square. Now y initial is 0, and the initial y, because it's thrown horizontally, so this part here is 0 as well. So y final, it's minus 60 equal to minus half 10 t square. From this, we can calculate the time t, which equal to 3.5 seconds. If we substitute this time back in this equation here, you will find x final equal to 13 multiplied by 3.5 seconds, which equal to 45.5 meters. Let's have this conceptual example here. From the same height and at the same time, one ball is dropped and the other one is fired horizontally. Which one will hit the ground first? Let's see this model. In this model, this ball is fired horizontally, and this one is just dropped. So let's see what will happen here. As we can see, both balls will reach the ground at the same time because they both have the same acceleration, which is in this case is g. So to answer this, both will reach the ground at the same time. Now, as another question, which ball will have greater velocity at the ground level? Clearly, the fired ball will have a greater velocity. So to answer this, the fired ball will have greater velocity.